On today's menu, you need to know that there are 3 edited videos for the lecture. You can download them separately for best results. They can be found on the website you have been using. And then they can also be seen in the links that are showing up as we're going on. For each video has 2 different links to the same video. So if you mix one, you can get it on the other one. So in this topic, we talk about joints in general. There were questions that arose last week when we talked about the joints that come from the as-built system. When you've already placed your drawings in their final positions, then you use as-built joints. Now, what happens when your drawings are not in their final position? What do you do? So we will discuss what you do under such circumstances today. And then after slides 1 to 9, there's a video demo to show you what exactly we are talking about. As before, we are using examples of, this time now we are using. Now, when we talk of general joints or whatever else we are doing, I deliberately use some specific examples, even though I'm using internal combustion engine. The reason why I chose that is because there are a number of complicated relationships in the drawings. The drawings themselves are simple, but when you put everything together, it looks formidable. But that is how virtually all drawings are. By the time you're able to analyze, pick them one by one, you'll see that once you can draw individual components and you can relate to them, no matter how complex something looks initially, it's no longer that complex at the end. So we are going to use the internal combustion engine example. We'll continue with that, with general joints, with the issue of joint origin creation, then the issue of location of your entities. When you create entities such as bodies, sketches, joints, and construction lines, construction planes, construction points, where do those things go? And we check whether they matter. Then we will see that they matter, and then we will see how you can repackage the way we have been drawing out for better solutions. And then we end today's class with an assembly of an inline engine. Again, that one has a video demo. We already saw that joints can be used to enforce kinematical or also called geometrical relationships that physically occur between components. We distinguish between bodies and components. Bodies are the visual representations of different objects. It's the body in Fusion 360 is a container, but components are also a container. They are also containers, but they are rough idealization of the parts you have in an assembly. They may not look different to you, but Fusion 360 treats the two completely differently. It is only in components that you can create relationships. You cannot create relationships in bodies. Bodies are just dumps. Just dump a body there and it is there, yakata. It doesn't really do anything and there's nothing you can really do with it. But in components, you can take one component and say it must have this kinematical relationship with another component. With that, you can have drawings that behave like real-life objects. If you don't do that, if you're just working with bodies, if you move them, they can be passing through one another, things that cannot happen in real life. So reality is far from just dealing with bodies. You have to deal with components if you want to implement some real-life motions and displacements in your design. So the components give a little bit more reality to what you are doing. Joints, strictly between components. If you need to implement a kinematic relationship, note they can only exist between components. Make components out of bodies in order to implement joints. We implemented as-built joints in the last lecture. Today, we're going to go further. We're going to go further and implement general joints. So you see how we can implement relationships when the graphics design that we have done is not necessarily in its final position. The joint, we place them in the correct position with the methods that are there in the joint. We implement so today we carry the matter further and implement general joints. As-built joints are good, but they are restrictive. They are very useful in their context. The context is narrow, and it applies only when the components are already in their expected positions. Otherwise, you general joints. Implementing general joints is not more difficult. It's not more difficult. It only requires more information because the joint process creates the final geometrical location as well as possible movements. So what you achieve in the general joint is more than what you achieve in as-built joints. That's why you need more information. In as-built joint, you already supplied the final location, so there lies the difference. There's less to ask for. So imagine if we have a piston pin, a cylinder, crank, connecting rod, and end rotor, all of them just scattered. You can easily do this by opening a fresh drawing and then copy all these objects from an existing drawing to it and just put them, just place them anyhow. And we can now use joints to put them in their correct positions as well as create the kinematical relationships between them. When we do that, then we are looking at general joints. So joints from arbitrary locations, when components are not arranged as they will be in their final locations, we make use of general joints. To achieve this, you create a new design, cut and paste new the individual components arbitrarily. Here, not how they should be eventually arranged. Can also get this by designing them in the arbitrary locations. Import them from other designs, such as other software, such as SolidWorks, Solid Edge, Inventor, AutoCAD, and so on. You can get these things. And then when you do that, then you can now begin to implement general joints, and you can still arrange them together as nicely as you did with the as-built joint. Now, if you look at this place, we can ask ourselves, how many components are there? Well, you can count 6, but if you count the pin and the piston as 1, then you count 5. So it's 6 in all, 5, if we consider the piston plus the pin as a single component. And that is what we shall do. How we do this matter. How it matters how we do it. And we can have the piston as a component with the pin as a subcomponent. We can also have a full piston with a component as a component with a pin and piston as 2 constituent components. These are 2 different ways. We have used the first one so far, where that we already have a piston, and then we now added a pin as a sub-component of it. Watch out for some effects of these choices as we see them later. Joints are in a component higher than components being joined. Serious implications in slides 14 to 19. So if you have a component containing other components, it's that containing component that is going to have the joints. So at this point now, we can watch the video that is here. I can click here, so you can do that on the downloaded video yourself. The advantage of your downloading it is that the loss in fidelity caused by going over the internet on Zoom is no longer applying to you because you have the original video too. So you can watch it here or watch it on your own.